Hey guys, hope you guys had a good weekend. We're going to be talking for section 5.5, bases other than E and their applications. Interesting homework assignment tonight. Page 368 slash 392, 1 through 33 odds, 41 through 93 every other odd, 95, 97, and 99. As weird as it looks, this is a relatively short section, but it's pretty dense. It's got a lot of material packed into it. And so I want to spend as much time as possible going through his examples. And to do that, we need to go quickly through our notes. So let's talk about the first thing in our notes, which is going to be this definition. So we're still talking about exponential functions. So this is a function. We talked before about the natural exponential function. Natural exponential function, which was e to the x power. E was a number. The number was 2.717. And so we talked about why it was natural was because of the derivative. It has a natural derivative that is equal to itself. Today we're going to talk about functions that fit a different form, and these are a to the x power. So examples of this would include things like 3 to the x power, or 9 to the x power, or in weird ways things like negative 2 to the x power, or even functions like 1 minus 6x to the x power. We're going to talk about all of these different types of examples throughout today. But let's start first with what the basic example of a to the x power actually means. It is equivalent to e to the natural log of a times x. So this is the classical definition and an easy way to get from base a into something that we already have an understanding for. And so this simple process allows us to take a function that is written in terms of a and write it as powers. Now, as you can imagine, this function can simplify some and allow us to get to other results. But for now, let's note a couple things here. First of all, some properties. Here's our big list. A to the 0 power is 1. That is, if you remember, because if you have something to a power, like 3 to the x power, that just means that you take 3 x times. Or if you have 9 to the x power, you would say 9 x times. Or if you have negative 2, you get the point. And so a to the 0 power means a function which has 0 a's, which would be a function of 1. So, our second property, a to the x, a to the y. We had a similar property for e's because e is just an a, that's very specific. That becomes a to the x plus y. We'll use these properties a few different ways today, specifically to simplify functions into one power, or to split functions apart so that we can shake them a little easier. 3. We had this one as well when it came to exponentials. A over x, a to the y, is equal to a to the x minus y. And then the last one's the power. A to the x power to the y power just becomes ax y. These properties allow us to convert a function from one form into another, and thereby allow us to change how the function is viewed. Note that for none of these functions, the order isn't really dependent, except for subtraction. So if you have a to the x times a to the y, you could put x plus y, but you can also put y plus x. And going backwards, you can do the same thing. Same with multiplication, because if you can write it in this form, you could, of course, write it backwards as being equal to a to the y to the x power. Now, when it comes to these kinds of functions, these are your basic properties. I want to do the log function at the same time. So let's look at the logs, which are the opposites of these. So we have the definition of a function base a. It is right here. And its properties. So let's talk about the definition of the logarithmic function. Base A. Now, we've talked about the natural log. Remember, the natural log was ln of x. But really, this is just log base e of x, the natural logarithmic function. Now, these logs, just like with any of these other functions, are going to have specific properties. And our example here, log base a of x is equal to 1 over the natural log of a times the natural log of x. This gives us a concrete definition for both these functions that links us right into natural logs or powers of e. And so at any point in time, if you see a log base a of x, you can rewrite it as this form. 1 over ln of a. Remember, ln of a would be natural log of a number, so this is just a number, times the natural log of x, which we already have an equation for. And same thing over here. We could then take this function combined with one of our properties to take this and split it apart into multiple components, which can then be taken derivatives of. So let's now look at the next piece, which is properties of logs. Just like with exponents, they have 4 properties. First property, log base a of 1 equals 0, which notice is the antithesis of the first statement over here. So a to the 0 power is equal to 1, so log base a of 1 is equal to 0. Remember, they're inverse functions. So if I plug in 0, I get 1. If I plug in 1, I get 0. They're opposites of each other. 2. Log base a of xy is equal to log base a of x plus log base a of y. Which again, you notice is just a version of this second property, where multiplication becomes addition, where in this one, multiplication becomes addition, just in different ways. One does it inside, it's multiplying outside to get something inside. This one is multiplying inside, and it gets something outside. That's the properties of inverses right there at play. Number 3, if you can imagine number 3's opposite, so log base a of x over y is equal to log base a of x minus log base a of y. And again, these are designed to be natural opposites. And then our fourth property, it's a fun one. Oh, we got these backwards. It doesn't matter. Log base a of x to the n power is equal to n log base a of x. You can put these properties in any order. They're all the same thing. And then last of all these, this is the one that's going to be really pivotal here. How do these all fit together? Okay. First thing. Y equals a to the x power if and only if x equals log base a of y. So you can always convert an exponential into a logarithm by using this formula. And you can always convert a log into an exponential. Notice that which one's isolated switches. So the y was by itself, now it's inside the function. The x was by itself, now it's inside the function. 2. A to log base a of x power is equal to x. So in other words, the a, which is a base, and the log, which is a power, cancel, leaving just x by itself. And this is true as long as x is greater than 0. And finally, the opposite of this, number 3. Log base a of a to the x power is equal to x for all x. So why are these restricted and this one isn't? Well, this one, the x is being plugged into a log, which has to stay positive. And so this log has to stay greater than 0 in order for this first one to work. But in this one, a to the x power is a number to a power, which will always stay positive provided that a is positive. And so this is one of those things where they have slightly different pieces that all fit together. Let's look at some homework problems. Try to see how all these pieces fit together. And I'm going to start with number 2. Okay. So for my first example, the function says evaluate the expression without using a calculator. It says log base 27 of 9. Okay, this one, I'm going to use one of my properties of logs to rewrite this. In fact, I'm going to use this inverse property here. So, in this function, I'm probably going to use this first one here. Either that, or I could... No, I think this is best. Okay, so I know this is going to be equal to a number. In this case, that number I'm going to make it equal to is x. So, using this idea, I can then come back and say, all right, which one of these properties is going to hold true? Well, I can convert this. This becomes, according to this first property, 27 to the x power equals 9. Now, in this form, it isn't easy to tell if the answer should be 2/3, unless you happen to know your power rules really well. But in case you're wondering how to get that answer without using some extra math, there are many ways to do so. First thing I could do is I could rewrite 27 as 3 to the 3rd power. I could do the same thing with the 9. And so from here, I can use my basic property, which states that 3 to the 3rd power, I can then combine these together to become 3 to the 3x equals 3 to the 2nd. This is one of my properties from over here, number 4. But notice I have to see 27 as a power of 3, and 9 as a power of 3. So seeing different bases is really important with these kinds of shortcuts. From here, I can then take the natural, or the log of both sides, log base 3 of 3 to the 3x equals log base 3 of 3 squared. Why would I do log base 3? Well, because if you look at your properties, log base 3 of 3 will cause the log and the 3 to disappear, meaning this piece goes away and this piece goes away, leaving behind 3x and 2. Then finally we divide. X equals 2/3. So notice that in this problem, we had to first take the log, convert it into an exponent, take an exponent and change the exponent using exponent rules, use exponent properties to rewrite it, use logs to cancel those properties, and then solve a simple variable equation. Not exactly easy, but notice how they all just flow from the different properties and properties of the actual exponent we had in the problem. Let's look at number 4. Same way. Number 4. It states log base a of 1 over a. Okay, let's do it. So like before, I'm going to make my first step set it equal to x. A good step here is usually to rewrite it, but you don't have to. And in this case, I'm not really going to. I'm going to do this as log base a of 1 minus log base a of a equals x. That's allowable using our property right here. Division becomes subtraction. So I rewrite the function as a subtraction sign. Now I can use this first property, which states that log base a of 1 is equal to 0. Log base a of 1 is going to become 0. Minus log base a of a. Well, log base a of a is actually equal to 1. And so now I can easily simplify. 0 minus 1 would be negative 1. X is x. Here's my solution. I could have also done this by converting to power rules. It just takes a little longer. So let's say I did the same way I did it with number 2, where I converted the log into an exponential. Well, in this case, it just makes it kind of weird, but let's go ahead and do it. This becomes a to the x power equals 1 over a. And from here, it's kind of obvious that it should be here. However, we could just rewrite a to the x power equals a to the negative first power, and then we could again use log base a on both sides and get x equals negative 1 the same basic way. And so these are the properties of logs. They allow you to fix a function and rewrite it in terms of something else. Let's now look at things like number 6. On number 6, it says write the exponential equation as a logarithmic equation or vice versa. Okay, well, let's look at 6. We have 27 to 2/3 power equals 9. And part B, which we'll do later, says we have 16 to the 3/4 power equals 8. Okay. So we're going to take this exponential, we're going to write it as a logarithm. So in this case, I'm going to use this property right here, which states that y is equal to a to the x power if only if x is equal to log a to the y power, or log base a of y. And so what we're going to do is the y in this case is going to be the 27 to 2/3 power, and the y is going to be the 9, which means that the x is going to be 2/3 and the a is going to be 27. So let's take a look. This would become, so remember, x is 2/3. My a would be 27, and my y would be 9. Which you'll notice this is the setup for question number 2. Sneaky. Part B, same basic way. So I look in here. I see that I have my number by itself, which I'm going to call y, my power, which I'm going to call x, and my number, which I'm going to call a. And so I just take this function written in exponential form and I'm going to write it in logarithmic form. This would become x by itself, so this would be 3/4 by itself, equals log base 16 of a number, which is 8. And in case you're wondering how this looks in a calculator, I actually have a calculator software that I downloaded. So it should be true that each of these is the same. So if I take 27 to the 2/3 power, it should equal 9. If I take log base 27 of 9, it should equal 2/3. And in fact, it does. Let's take a look here. Take out my nice calculator here. Let's go ahead and do this. So I'm going to take the first one, which is 27. Every time. 27 to the 2/3 power. It should equal 9. Oop, there it is. Now, if we use the same thing, we can do log base 27 of 9, and it should equal 2/3, or 0.6 repeating. For this one, there is no log base a in your standard TI-84 calculator, and for many calculators, there isn't a log base a. For the TI-84s, and for those like it, if you go into the Math tab, one of your options in the Math tab is log base, which allows me to type in 27 and 9, and I get 2/3 exactly as expected. Same thing with the other one. If I take 16 to the 3/4 power, I should get 8. And if I take log base 16 of 8, I should get 3/4, which is 0.75. There it is. This is the definition of a logarithm and how it fits together. Let's now look at number 8. Showcasing it the other way, just so we can get some extra practice. Number 8. Okay. With each of these, a big detail is going to be, do you understand and can you use the properties? Because if you don't, it's going to cause problems. So let's go ahead and take a look at number 8. It says we have log base 3 of 1 over 9 equals negative 2. And for part B, we have 49 to the 1/2 power equals 7. All right, let's do this. So in this function, let's take a look at what happens. We have, in this function, a base, a number, and a number outside. According to my list of properties, I can invert this log and turn it into an exponential. In this case, 3 is going to be my base, so it's going to be my a. The 1/9 is going to be my y, and the -2 is going to be my x. Just following the same basic form as our properties here, which means that I would have as my new function 3 to the -2nd power equals 1/9, which this is hopefully obviously true. 3 to the -2nd power would cause it to drop to the denominator. 1 over 3 squared. 3 squared is 9. 1 over 9, done. On the other one, 49 to 1/2 power. Well, this should be obvious as well as being true, but let's write this as a log. So just like before, let's note our components. We have our base, which we're going to call a. We have our power, which we're going to call x, and we have our result, which we're going to call y. So how do we write this? We would say log base 49 of 7 equals 1/2. And you can verify that with a calculator pretty easily. So there we have it. This is how you simplify a logarithmic expression or an exponential expression, or rewrite it using inverse properties. These ones are really big details to have, and so make sure you note how they kind of fit together. Now, the secondary component we need to talk about is how to solve with these, because it's not just enough to be able to use them and verify the properties are true. They are. But now we need to actually be able to solve something with them. So let's look at 4 more problems. 20, 26, 30, and 32. Okay, so we're 20. On number 20, we have the following equation. Solve for x or b, depending on the problem. I need to zoom in a little bit. I can't really see it. There we go. It says for part A, log base 3 of 1 over 81 equals x. Now, with enough practice, I know the answer is -4, but let's showcase how to use properties to get to that answer. So, first steps. I'm going to take this function, I'm going to perform a rewrite using inverse properties. It's really common to not like the way the function is given to me, and so a good way to fix it is to rewrite it using properties. And this is one of the properties we're going to use. So I'm going to use this property right up here. I'm going to convert this into power form, so, or exponential form, it's more commonly called. And so how do I do that? Well, I need to know what my a is. My a is going to be 3. I need to know what my power is going to be. That's going to be my x. I need to know what my number is going to be, which is going to be my y. So let's do this. So we have 3 to the x power equals 1 over 81. Now, a common way to go from here is to rewrite again with the same base. Now, 81, you might think of 81 as 9 squared, but I do not like that one here because they have different bases. This has a base of 3, this is a base of 9, those are not the same. And so what I will do instead is I will write 3 to the x is equal to 1 over 3 to the 4th power. Because 3 to the 4th power is 81. If 9 squared is 81, then 3 to the 4th is 81. You can use the properties like this one to show that's always true. From here I can rewrite again. If there's a power on bottom, I just have a -4th up there. And now hopefully it's obvious that x equals -4 from here. But I'm going to go ahead and show it. I'm going to now use logs to cancel exponents. How do I do that? I have to use the same base on both sides in order to make this work. That's why I need this 81 to be base 3. Because if it's 81 and 3, if I choose log base 3, it's going to cancel this 3, but it's not going to cancel this 81. If I have 3 and 9, it's going to cancel the 3 but not the 9. But now I have 3 and 3, so it's going to cancel both 3's, leaving just the x's. This is equivalent to log base 3 of 3x, log base 3 of 3 to the negative 4th power. Remember, bases and exponents of the same base cancel. So 3 and 3 we're going to cancel, leaving just x equals negative 4. You can get that same solution just in a slightly different way if you're willing to do the properties up here. So I'm going to showcase this one more time. I'm going to do a again. So I do log base 3 of 1 over 81 equals x. Well, what I could do instead is rewrite it as powers of 3 here. So this becomes log base 3. I'm going to use the work I already did, the shortcut sum of 3 to the negative 4th power equals x. And then just like before, log base 3 and the 3 will cancel, leaving negative 4 by itself equal to x. This way is a lot faster and easier, but you have to see it. And so there it is. Let's talk about b. So on b we have log base 6 of 36 equals x. So now, I could do exactly what I did just a second ago. Rewrite this 36 as a power of 6, and then try to solve. Or I could instead, try to use the log properties and inverses to solve for it. I'm going to do it the fast way this time. This becomes log base 6 of 6 squared equals x. And then hopefully it's obvious here, log base 6 and 6 are going to cancel, leaving just 2 and x. This way is much faster and easier if it's a function that can be rewritten in the same base. So we got lucky. 36 is 6 squared, so they have the same base. 1 over 84 is 3 to the negative 4th power. They have the same base, 3 and 3. What we're going to see next is we're going to look at example 26. These are examples where they aren't as nice, and where you kind of have to use the properties to rewrite them. Otherwise, you can't really get an answer. So, 5 to the 6x power equals 8, 3, 2, 0. Now, there's a lot of ways I can do this, and I'm going to showcase the most common way. I want to get x by itself. What's involved in getting x by itself? Well, I have this 5 that I need to get rid of, and I have this 6 I need to get rid of. According to order of operations, this one I need to get rid of first. And this one I need to get rid of second. Remember, please excuse my dear Aunt Sally. So please, parentheses has to go first, then exponents. This is an exponent. It's 5 to the 6x power. I got to get rid of that exponent first. How can I do that? Logs. I do log base 5 of 5 to the 6x power equals log base 5 of 8, 3, 2, 0. Now, log base 5 of a number is going to be another number. We don't know what that number is yet. We can find it fairly easily in just a moment. So, log base 5 of 5 is going to cancel, leaving just 6x by itself. On the right-hand side, we have log base 5 of 8, 3, 2, 0. From there, we want to get x by itself, so we do that with division. Divides both sides by 6. We get x equals log base 5 of 8, 3, 2, 0 over 6. Now, log base 5 is a number. I'm now going to come in and use my TI. Let's do it. So I do log base 5 of 8, 3, 2, 0. Oops. There we go. Divided by 6. And we get an answer of 0.93. Said 3 decimal places in the instructions. Yep. 935. Rounding correctly. Just like with any other mathematical problem, my goal is to get x by itself, but I do so by using these properties to get x by itself, as opposed to any other method that I choose. Okay. So 30. 30 states. We have 1 plus 0.10 over 365. That's a weird formula. To the 365t equals 2. Now, this is a standard formula in something called compound interest. We're going to talk about that at the very end of the section today. It's really standard, and so don't look at it like it's crazy. All right, let's do this. So as before, I'm going to log both sides. I can choose the base to be 1 plus 0.10 over 365. .365t. So I make sure to log both sides with the same base. Now on the left-hand side, these two are going to cancel, leaving just 365t. Okay, now from here, all I have to do is figure out what t is by division. So I'm going to take both sides, divide by 365. I end up with t is equal to log base 1 plus 0.10 over 365 of 2 all over 365, which is going to be a number, and then calculator time. Can't get out of the calculator here. So I'm going to use the exact same thing I did before. I'm going to go to log base b, and I type in the equation 1 plus 0.1 over 365, and then inside I would do 2 all divided by 365. So what does that tell me? It tells me we would have 6.932 rounded. And there we have it. Now the same basic thing's done with number 32, just going in the other direction using a log, but you can get the idea really quickly. Okay, so we've talked a lot about just the basic formulas, so now let's talk about something more advanced, the actual rules that make it calculus. So how to take a derivative and how to integrate. Well, here's our integral properties, our derivative properties. Next piece of notes. Theorem 513. Theorem 513 states, four different variations on how to do a natural logarithm, or how to do a non-natural logarithm. So these are your derivatives of bases other than e. Let's go through the four. 1. If I have a to the x power and I wish to take a derivative, it is equal to the natural log of a times a to the x power. Remember, a is a number, so the natural log of a will also be a number, and then a to the x will just be a to the x. 2. If I wish to take a derivative with respect to x of a to the u power, so this is assuming we're going to be doing some u substitution today, we would do ln of a times a to the u times du dx. This is basically just the chain rule. 3. So we've done a to the x power and a to the u power. Now we need to do log base A of x dx is equal to 1 over ln of A times x. And then part 4, if I take a derivative of log base A of u, be 1 over ln of A times u times du dx, or as more commonly written, this would be u prime over ln of A times u. And so this gives us some ways to take derivatives of both exponential and logarithmic functions. Notice that we have examples using both a to the x and a to the u, or log base A of x or log base A of u. And so we can, as long as we can put it into one of those forms, we can always take a derivative. A consequence of this theorem, let's assume A equals E. Well, then according to number 1, if we let A equal E, we'd have the derivative with respect to x of e to the x power. Now we already know that should be e to the x, but let's see why this formula still works. This would be ln of e times e to the x. Well, guess what? Ln of e is 1. And so it still works. That's why e and ln are so necessarily talking about first. If I was to do the same thing over here, let a equal e, then take the derivative with respect to x of log base e of x. This would be equal to 1 over ln of e times x, which we just said, ln of e is 1. 1 times x will just be x. Which also means that this is equivalent to the natural log of x. So log base e of x is equivalent to the natural log of x. And so these 4 can do everything that the e's can do. It's just e is faster. And so if you see an e, you should probably use the e formulas. Anything else, you should use these formulas instead. Okay, let's do some problems. Let's take a look at, these ones in here. All right, start off nice and slow. Note the hint that it gives you in the problem. It states you may wish to, on some of these problems, rewrite these using exponential logarithmic rules first. That's a good suggestion for a lot of these problems, but not for all of them. Okay. So, this one, I'm going to do 42. I'm actually going to do it twice real quick, showcasing kind of why rewriting them can be so helpful. This says f of x is equal to 3 to the 2x power, and it says what's f prime. Well, what I can do here is I can let my u equal 2x, which means my du dx is equal to 2. So from here, let's go ahead and solve our problem using a chain rule. So we would do ln of 3 times 3 to the 2x power times the derivative, which is 2. Or f prime of x is equal to 2 ln of 3 times 3 to 2x power. Now, on 42, the cool thing is we could have used a property to make this a little simpler from the start. The property I'm going to use here is actually this property. It states that I can take any multiplication and split it into a combination of multiple multiplications. Actually, I think I'll use the other one. Okay. I lied. For this one, there isn't really a great way to rewrite it. It's just the best way to do it here. Okay. Man, on a roll today. All right. Let's now look at one like 46. So, as with many of these problems, you can guess they're going to use multiple different rules from previous chapters. So you're going to have to make sure you know your chain rules, your product rules, your quotient rules, your power rules. Make sure you know all of those, because it's difficult to do ones like 46 if you don't know your product rule, for example. So 46, we have y equals x times 6 to the negative 2x power. Okay, I see my problem. I have multiplication. Multiplication in the problem indicates to me I'm supposed to use the product rule, so that's exactly what I'm going to do. I'm going to take this function and apply the product rule to find the derivative. So, y prime is equal to, I would do left times the derivative of the right, which I will leave right now as just the derivative of the right, plus right times the derivative of the left. Now let's simplify. So x would just be x, the derivative of 6 to the negative 2x power. Okay, that's a chain rule. So I would do ln of 6, using that first property up here. I would do ln of 6 times 6 to the negative 2x power times, using the second property here, u prime, which would be negative 2. So this is all 6 to the negative 2x prime. It's all of this stuff. Plus 6 to the negative 2x power times x prime. X prime would be 1. And so I end up with the following. I rewrite. This should be ln of 6, not ln of x. Why am I being dumb? ln of 6. So ln of 6 is a number. Negative 2 is a number. So I'm going to move those both out front. Negative 2, ln of 6, x, 6 to the negative 2x power, plus 6 to the negative 2x power. This is one version of the answer. Of course, another version would be to factor out the 6 to the negative 2x power and get negative 2 ln of 6x plus 1. Or, of course, it's opposite, 1 minus negative 2 ln of 6x. So all these are acceptable answers here, but I prefer this one because it's the easiest to get to. The bottom one is also acceptable, though. There's 46. Notice how we had to use not just our E rules, but also our product rule. Okay, let's now look at 50. Okay, as we go farther and farther, I'll try to use less and less rules. So we have, fun one, g of alpha. We haven't used alpha a whole lot this year, but alpha is just another variable, equals 5 to the negative alpha over 2 sine of 2 alpha. So, just like with the previous problems, we have multiplication, so I'm going to use a product rule. Well, let's do it. G prime of alpha. So I would do left 5 to negative alpha over 2 times the derivative to the right, which would be sine of 2 alpha prime, plus the right, which is sine of 2 alpha, times the left, which would be 5 to the negative alpha over 2 prime. Alright, let's do it one piece at a time. So this would become 5 to the negative alpha over 2 times derivative of sine is cosine. The derivative of 2 alpha would be 2. This becomes 2 times 5 negative alpha over 2 cosine of 2 alpha plus sine of 2 alpha would just be sine of 2 alpha. The derivative of cos of 5 to negative alpha over 2 would become the natural log of 5, which remember is a number, times 5 to negative alpha over 2. This would be our u, and so we times it by u prime, that would be negative 1/2. And then we just write all our pieces out. So this plus sign should really be a minus sign. Negative 1/2 and ln of 5 can move out front. Negative 1/2 ln of 5. We would then do 5 to negative alpha over 2 sine of 2 alpha. Or just like on the previous one, we could factor in 5 to negative alpha over 2 out of both pieces and get a slightly different answer, but they should all be the same. And so there's 50. Notice that we're using rules from previous chapters combined with rules from this chapter, as is common in calculus, to use multiple pieces from multiple chapters. Okay. Let's talk about one where it might be easier to rewrite first. (58). For 58, we have the following function. We have log base 10 of x squared minus 1 over x. And this is y equals. Okay, we do have an option. We could just start going with our rule. Remember, our rule would state, for my properties, we would do 1 over ln of a times u times u prime, but the u in this case is a fraction, and so u prime is going to be weird, u is going to be weird, like this isn't looking fun for this particular problem, and so instead I offer you an alternate solution. Instead of trying to do it the way it is now, I am going to rewrite the function using properties of logs. So we have a property of logarithms, which states that division becomes subtraction. So this is equivalent to log base 10 of x squared minus 1 minus log base 10 of x. This is much easier to do the two pieces for, and will give us the same solution. So y prime will be equal to, now I use my theorem. My theorem 513 states that I would have 1 over ln of 10 times x squared minus 1. Multiplied to that, I want to do our u prime, so that would be x squared minus 1 prime minus log base 10 of x would be 1 over natural log of 10 times x. This is looking pretty good here. And so y prime would equal to x squared minus 1 prime would be 2x minus 1 over ln of 10 times x. This way is so much easier than if we tried to do the original one. So using your properties can really reduce the amount of work you have to do, but then that means you have to know your properties really well. Let's do one more before we move on. 64. So 64 is a secondary type, where we're asked to find the equation of a tangent line. Just to remind us of how we do that, to find the equation of a tangent line, we need to first find the slope. Then we need to take the slope plus a point, and we need to then plug it into slope or point slope form. So let's go ahead and do that. On 64, the equation we have is y equals 5 to the x minus 2 power, and the point in question is 2, 1. Let's do it. Y equals 5x to 2 power, so y prime would be equal to, let's see, ln of 5 times 5 to the x minus 2 power times the derivative of x minus 2, which is just 1. And so our slope generating function would be ln of 5 times 5 to the x minus 2 power. We then want to find specifically the y prime value at this point, so we take the x value and plug it in everywhere there is an x. Let's see, we have 5 minus 2, so we have the natural log of 5 times 5 to the 2 minus 2. 2 minus 2 is 0. 5 to the 0 power is 1. So this tells me that the slope at 2 is 5. Okay, well, I've got a point. I've got my slope. I can now plug into point slope form. And for this one, I'm not going to simplify very much because I have the natural log of 5. It's not going to be a nice number. So I'm just going to leave it the way it is. Y minus 1 equals our slope, ln of 5, times x minus 2. That is one good answer. If you really wanted to simplify, though, you would have y equals ln of 5 x minus 2 ln of 5 plus 1. The alternative answer. And to verify this is in fact the tangent line, let me go ahead and pull up my calculator again. So go to my graph. My graph would be original graph, which is 5 to the x minus 2 power. Let's take a look at what it looks like. There's my beautiful graph. Yay! Okay, now let's pull it in the tangent line and make sure it actually fits that graph. So, my tangent line is y equals the natural log of 5, so natural log of 5 times x minus 2 ln of 5 plus 1. If this is correct, then at the point 2, 1, it should be tangent. Let's take a look. So in this case, 2, 1 is right here, and that looks pretty darn good. I mean, it represents the slope at that point, and it seems to only touch right there. You can see right here that at the value of 2, we have the same value of 1 and 1. And so you know it's going through that point, and it does look like the tangent because it is going up and to the right. And so this would be the equation of the tangent line as expressed in our function. So there we have it. This is how you do those kinds of problems. Now, there is also a way to integrate these kinds of functions. Let's go ahead and take a look at that real quick before we finish. In this case, I would direct you to page 365. There it is. This is a common integral that I would make sure is in your notes, which is what I'm going to do next. So, this will be my next piece of notes. It states the integral of a to the x power dx is equal to 1 over ln of a times a to the x plus c. The trick is to get it in this form. If it's not in this form, then we don't have a good integration process for it. And so you can see in the example right there how that works. Do note that the power rules are really helpful for some of these, because in some of these problems we're going to be using power rules multiple times. And so let's now look at our next two, which is number 76 and number 80. Okay, number 76. Okay, for number 76, I would strongly recommend using the definition of a natural integral. Either find a way to rewrite it using this process, which is already of a to the x power, and you can just rewrite it. Like 75 is a great example of one where it's already in a good form. But if it's not in a good form, the best thing you can do is to rewrite it using this process instead. So that's what I'm going to do. Let's now look at number 76 and number 80. But for most of them, I'm probably going to use that form to do it with. or some variation on it. Okay, so 76. We have the integral of 5 to the negative x power dx. So what I'm going to do here is this is going to be my a, this is going to be my x, and I'm going to just plug those into this other form. So this becomes the integral of e to the ln of 5 times negative x dx. Now, from here, I can rewrite one more time, integral e to the negative ln of 5x dx. What I can do now is I can use a u substitution and solve this problem like normal. So a u in this case would be negative ln of 5x, which means my du would be negative ln of 5 dx. I don't have ln of 5 dx, so I can divide. I would get du over negative ln of 5 equals dx. Everywhere there's dx, I'm going to replace with this. Everywhere there's negative ln of 5, I'm going to replace with u, and now I can integrate. Integral of 1 over negative ln of 5 e to the u power du would be 1 over negative ln of 5 e to the u power plus c. And then everywhere there's a u, I just replace back. So this is equal to 1 over negative ln of 5 e to negative ln of 5 plus c. If you take the derivative of this function, you will eventually get back here, but you will have to convert it, just like we did with this one. So if you take a derivative, negative ln of 5x, we would multiply out front, which would cancel with this negative ln of 5, leaving just e to the negative ln of 5, which is what we have here. And we already know that this is equivalent to that using our property. And so this is just a different way to do an integral. Notice that there's no direct way to get from 5 to negative x power to here without using e's. It's just not possible. And so, there we have it. Next, let's look at number 80. Same way. Number 80 is a little different because you don't actually need to do it that way. You can actually just directly do it as long as you're willing to do a u substitution. So number 80, we have the integral of 3 minus x times 7 to the 3 minus x squared power dx. I'm going to do a u substitution where u is equal to 3 minus x squared. That means my du would equal to 2 3 minus x times negative 1. Don't forget to take the derivative of the inside. So this would become dx. I don't have a 2 or negative 1 over here, so I can move those both over. So over negative 2 equals 3 minus x dx. I have 3 minus x and dx in the problem. So I can do a simple substitution now. Integral of 7 to the u power times du over negative 2. I could then integrate directly using our property we had on that previous page. This would become 1 over ln of 7 times 7 to the u power plus c. The negative 2 would be multiplied to the entire thing, leaving us like this. And then we perform a simple substitution everywhere there's a u. We replace. This become 1 over negative 2 ln of 7, 7 to the 3 minus x squared power plus c. And there we'd have it. Just a combination of substitutions, just like you would see in any other problem in this section. The last thing I will tell you is that in your homework, you happen to have some problems that deal with two very specific formulas that are in your book. If you look right here, page 366 would be the next thing I would put in your notes. So where are my notes? Where are my notes? Where are my notes? There are my notes. Okay. So, the next thing I would put in my notes would be this interest formulas. So, these are both dealing with compound interest, just evaluated in two different ways. Those two different ways would be A equals P parentheses 1 plus R over N to the NT power, and then 2 A equals P E to the RT powers. So this is N times per year, and this is continuously. For the last couple of problems in your homework, these involve questions about doing these kinds of problems, and so I'm just going to jump straight into the last problems. So I'm going to do example 98 and show how to use these formulas for it. Let's go to 98. Here we go. For the exercises, complete the table by determining the balance A for P dollars invested at rate R for T time for T years and compound N times per year. Okay. So this is a lot of plug and chug for 98. Basically, it's going to turn into doing a table. Let's kind of showcase how this is done. We have N over A. We have for 1 time per year, 2 times per year, 4 times per year, 12 times per year, 365 times per year, and then continuously. Okay, so for 98, we have P equal to $2,500. We have R equal to 6%. We have the total number of time is 20 years. Okay, well, let's talk about these formulas. So for these ones, I'm just going to list out the formula. I'm not going to get the answer for each one. So we would take P, R, and T and plug them in. But for this, we have N equals 1, 2, 4, 12, 365. That's going to all involve the top formula. And for this last one, we're just going to use the bottom formula. So let's take a look. For this first one, we have P is 2,500 times 1 plus my R, which is 0.06, over the number, which in this case is 1, to the N, which is our number, which is 1, times T, which is 20. Whatever number this is, it goes in that first box. For our second box, same basic way, 2,500 times 1 plus our rate, 0.06%, divided by the number, which is 2 times 2 times 20. Whatever that number is, goes in the second box. So this is the principal, or the starting amount. This indicates the percentage rate. This indicates the time per percentage rate. And this will generate our overall accumulation of money. So, 4, same basic way, 2,500, 1 plus 0.06 over 4, 4 times 20. Same with 12, same with 365 for this last one. This last one would be 2,500 times E to the 0.06 times 20. Whatever numbers you would get from each one of these, that's your solution for this problem. And so this is just a reminder of compound interest from like Algebra 1, because it does come up on the test occasionally, and they want to make sure you have it. So there it goes. That's it for this section. Section 5.5, dealing specifically with exponential and logarithmic functions of different bases and how to find those values. We have 2 sections left in this chapter, so keep that in mind. We will have our review and test this weekend, but that'll be it. If you guys have any questions, let me know. I'll be happy to answer any one of them, and I'll talk to you guys later.